Hello everyone and welcome to Texas Tech University's Project Lab 1 tutorial video. I am one of the tutors for this course. My name is Daniel, and in this video I'm going to be showing you how to use the inductive proximity sensor available in the stockroom and how to input the signal into the BASYS board. Okay, so to get started, we will look at the sensors that are available in the stockroom. Just to get a quick overview on what they look like, it is this metallic body sensor with the orange tip. It has 3 wires, a blue one, a brown one, and a black one. So the nomenclature of the sensor is this LJ18A3-H-Z, and then there's the AX, PX, CX, and several other models. So if you download this PDF, it'll take you to the data sheet. On the data sheet you'll see that this one is actually a conductive proximity sensor. So internally, the inductive proximity sensors would have an inductor to determine the change in magnetic field, and the conductive would have some sort of capacitor to determine the magnetic field. Looking through the data sheet, there's this one-page sheet is for the several different variations that it has. We have the LJC18A3 right here. So you see that is the NPN type. The BX would be the normally open, and the AX would be the normally closed. We do have the BX. So ours is in a normally open configuration. And looking at the sensor itself, let me show you the image. Up at the top here, this silver and blue band that wraps around it, it actually has a lot of information on the sensor. The image kind of looks like these right here. It does tell you if it's an NPN or the PNP type, and it tells you that the brown wire is positive, the blue wire is negative, and then your black wire would be your signal. So we do have this set up right here, the NPN normally closed. I'm sorry, the NPN normally open, as we saw in the data sheet. We have the BX, which is the NPN normally open. So that would be this image up top. And if you look at that label on the sensor, you will also see that it requires an input voltage of 6 to 36, and it runs at a current of around 300 milliamps. So again, the first step you would want to do anytime you are dealing with any hardware is to know exactly how it works. So first place you go there would be the data sheet, and now would be to get your multimeter, get your power source, and utilize the device to see what voltages and how it operates. So using this rechargeable 9.6 volt battery that is available in the stock room, we are going to power our inductive sensor, and we're going to measure the voltage on the signal leg to see what the voltage is. Real quick to talk about this 9.6 volt rechargeable, from personal experience I have found that fully charged this thing does go up to 11.5 volts, and when it drains it does go down to 7.5 or 7.6 volts. So if we hook it up to our multimeter, so if you see my setup, I have green jumpers connected to my negative terminal on a multimeter, and red jumper that is connected to my positive terminal on my multimeter. So hooking up my battery to my multimeter, I see that I have 10.78 volts on my battery. So 10.7 is between the 6 and 36 that this sensor needs. So if I plug in my negative to a rail and my positive to another, just a rail, and then plug in my brown, which is my positive, and then my blue, which is my negative, I can power my sensor and it should work. So, looking at the sensor itself, on the back there is a little LED, and as we put a metallic object in front of it, the LED does turn on. So now we see that the sensor is being powered and it seems to be working the way it's supposed to. So now the next step we want to do is to see what our output voltage is on the signal leg. So using my red jumper here again, I will plug it into the signal leg, and my green jumper I will hook up to the negative terminal. So now that I'm hooked up, with the appropriate voltages. So again, my red wire is just hooked up to the signal leg, my green wire is hooked up to the negative terminal, and as we add a metallic device in front of it, let me move. Try to get rid of this glare. So now we see that when no metallic objects are being detected, we have a 8.63 volts, and when it detects a metallic object, it goes down to 0. So 8.63 from a 10.78 input voltage. So with that in mind, the next thing you want to do is think about your BASYS2 board. So how are we going to take the signal from this sensor onto the BASYS2 board? So if we look at the data sheet for the BASYS2 board, which I hope you all have, you will see that the PMOD ports can only take a voltage up to 3.3 volts. Anything higher than the 3.3 will actually burn and damage the internal components of the board. So it is very important not to input any voltage higher than a 3.3. And you also have to make sure you don't enter any current into the BASYS board. Alright, so now we can identify issue, which we have signal coming off the center of a 8.3, and we need a 3.3 to go into the BASYS board. So a few different things that came to mind, or that I have seen in the past year or so that I've been a tutor for this course. One method is to use an optocoupler. An optocoupler is a little IC chip as seen here on the right hand side. These chips are available in the stock room, and as you see, you have two separated sides. So here we have a high side, 1 and 2 would be your high side, and as current flows through your high side, photons would be released from this photo emitter, and then this photo detector will detect those photons and allow current to flow on the low side. So your high side would be your 8.6 volts, and your low side would be your 3.3 volts. And as current flows on your high side, it'll allow current to flow on your low side also. So that would be one method of entering your high voltage into your safely entering your high voltage into your BASYS board. Another method would be a relay. So a relay works similar to the optocoupler in that it has a high side and a low side, that if current flows on the high side, it allows current to flow on the low side. So looking at this most simple relay up here, the single pole, single throw, we see that the high side has an electromagnet. So as current flows on the high side, it charges this electromagnet, creating the electromagnetic field that will physically close the switch and allow current to flow on the low side also. So you had current flowing on the high side, will allow current to flow on your low side, similar to the optocoupler. On the relays, it is important to figure out which configuration you have and to figure out if you are using it in the normally open or normally closed setup. Alright, another method that I thought you could use would be a comparator. So a comparator uses an op-amp to tell you when something has changed below a certain voltage reference. So typical comparator circuits can be seen in the data sheet for the LM339 comparator, or there's plenty of online resources for a comparator. But the basics of a comparator is you have your signal going into one leg and your voltage reference going into the other leg, and when your signal goes below your voltage reference, the output will reflect it. Alright, so the last method I wanted to talk about would be a voltage divider. So as you know, you can make an output voltage so you can calculate any output voltage that you want based on a couple resistors and an input voltage, as shown in this resistive divider setup Wikipedia page. So if you have a known VN, you can set up some resistors in this configuration to get a Vout that you want. So in our case, we do have a known VN. That would be our power supply, and we want a Vout of 3.3. However, it is very, very important that you don't use this rechargeable battery as your VN. As your VN is shown in this resistor divider network. Because if you think about it, that battery changes from 11 point something volts to 7 point something volts. So if this VN changes, that means this Vout changes. So if you thought you had 3.3 volts, as your battery dies, it actually changes its volts to probably be below recognizable for the BASYS board. So if you want to do a resistor divider network or voltage divider network, you're going to have a stable VN that can create a stable Vout regardless of the status of your battery. So what that means is that you can do a voltage divider, but you just need one extra component of a voltage regulator. A voltage regulator will regulate your battery to be a regulated voltage that can stay within a certain range and provide the output of within a certain range. So what I did is I used the LM7808 regulator, So here's the data sheet for the L78 L series regulators. So there's the 3.3 regulator, 5 volt regulator, and 8 volt regulator, all in this specific package. We are using the TO92 package. It has pin 1 is V out, pin 2 is ground, pin 3 is V in. On this test circuit, it does show you that you want a 0.33 microfarad capacitor on the input to ground legs, so 3 to 2, and a 0.1 microfarad capacitor on the output to ground legs, so 1 to 2. These capacitors are pretty important, so we know that Vn can change from 11 down to 7, and these capacitors prevent any drastic change on your output. So the regulator, you want it to regulate a specific voltage, so these capacitors allows it to regulate it without having to change based on the Vn. In future labs, you'll also see that these capacitors remove a lot of noise that are inherent with power supplies. So again, grab these two capacitors and add them to your voltage regulator. And this voltage regulator, I grabbed it from the stock room. Plenty of them available. As you see, there's maximum ratings, and then there's additional characteristics. For the additional characteristics, you do want to make sure you're looking at the 7808, which is this page, to look at all your outputs and regulations and current and everything you need from this regulator. Alright, so looking at my hardware setup now, we can see, so let me unplug this and this and unplug these guys. So on my breadboard here, you can see that I have two regulators up at the top here. This one would be my 8 volt regulator. Input voltages are right here. My two capacitors that I need are right there, and my output voltage goes to my rail. So providing the input here, I have 8 volts across this rail that I can use. Here on the left side, I have a 3.3 volt regulator that produces 3.3 volts on this rail, and I would use that to power the BASYS2 board. So 8 volt regulator, 3.3 volt regulator, and to power both regulators, we will use this 9.6 volt rechargeable. That again, we saw it was charged up to 10 something. Alright, so that's a quick setup there. Powered up both of our regulators. First thing I always do is to check the power on our regulators. So using a multimeter and these two jumpers, I will check the right side. Right side is the 8 volt regulator. As you see, we got a 7.92. It's good. And now the left side, it's our 3.3 volt regulator, which you see we have a 3.26, so which is also good. So now we have our voltage regulators being powered and supplying the appropriate voltages. So now that we have a regulated 8 volts, we can plug in our inductive sensor to those 8 volts. Again, blue one is ground, so I'll plug in blue one, and brown one is positive, so I'll plug in black one, and giving it a quick test on our sensor. You will see that the LED is turning on when it's supposed to. So it is being powered correctly. off the 8 volts. It's acting the way it's supposed to. So the next thing we want to see is now what the voltage output of the signal is. So hooking up my positive terminal of my multimeter to the signal leg, I will see that the output of the signal leg is at a 5.84. Alright, so that's something to keep in mind when we give it an 8 volt input source to the sensor. The signal outputs a 5.8 volt signal. Alright, so again, it's still acting the same way, where 5.8 would be when it does not detect anything, and 0 would be when it does detect something. 0, 5.8, 0, 5.8. So with that in mind, now that we have regulated the input voltage of the sensor, we have it regulated to an 8 volts, and we have in mind that our output, our signal leg, is at a 5.84. Now we can do a little bit of voltage division. So looking at our voltage divider network setup here, we see that we need an R1 and an R2, and we have our VN and Vout. Vout, as shown, will be measured across R2, and the equation for Vout is Vn times R2 over R1 plus R2. Alright, so if we want a Vout of 3.3, and we have a Vn of 5.84 as shown on our multimeter here, so the ratio that we need for our resistor setup, R2 over R1 plus R2, is a 0.565. That ratio is shown here, is found by dividing 3.3 by 5.84. Gets your 0.565. 0.565 can also be written as 56.6 over 56.5 over 100. That is equal to the ratio R2 over R1 plus R2. Now if we pick a large R2, it is important that you pick large R's because of the biasing of the NPN transistor. You need large R's in order to bias your transistor correctly. So picking a large R of 470 kiloohms, we can cross multiply, find out that R1 plus R2 equals to 100 R2 divided by 56.5. If we do that math real quick, it ends up to R1 plus R2 equals 832 kiloohms. So since R2 is 470, we can subtract R2, finding that R1 needs to be 360 kiloohms. So for our R1 and R2, we have found the appropriate resistor values that they need to be in order for us to get Vout that we want. So going to stockroom again, grabbing a 360 kiloohm resistor and a 470 kiloohm resistor. I have set up our voltage divider right here. So that is R1 and R2. R2, as shown in our diagram, goes to ground. So R2 goes to ground. And to measure our Vout, we're measuring at this junction where the two resistors meet. So the Vn is going to go at this other side of this resistor. So to do that real quick, grab the signal leg, put it into the input of this voltage divider network, and now grounded. Alright, so now we can go ahead and measure off our node right here. So grabbing the red terminal, connecting it to that node. we can see that now our voltage when the sensor does not read, when not detect anything, is at a 3.3, and when a metal is present, it will drop down to the 0. 0, 3.3, 0, 3.3. No additional voltages are being generated, so therefore that point right here is now a safe input to take into our BASYS board. So now that we have regulated our voltage and created a safe input to take into our BASYS board, it is now time to power and program our BASYS board. So opening up our Xilinx ISE. We'll open up the 32-bit navigator. So now that the ISE is open, I will file new project. Call this IPS tutorial 2 HDL type. Hit next. These settings, you can set these, verify that they're set, hit next, hit finish, and it'll open up an empty project. Here you can double right click on this hierarchy, empty view, hit new source. You want to select Verilog module. Again, I would call it IPS underscore tutorial 2. Hit next. Our input is going to be called signal, and our output is going to be called LED. So hit next, finish, and it'll pop up this template module for you with the standard timescale, standard heading, and we see that we have one input, one output. So a quick module would be assign LED, which is the output, equals to not signal. So the tilde sign is just not operator or an inverter. So as you see, signal is an input. It will be a binary input. It'll be a 0 if the voltage is close to 0, and a 1 if the voltage is close to 3.3. So from what we know of our sensor, it gives a 3.3 when it does not detect anything. So when it does not detect anything, the 1 gets inverted to a 0, and when it does detect something, it goes down to 0, which gets inverted to a 1. So one line there, that's all you need. Hit save and synthesize. It'll run synthesis real quick. Shouldn't take more than a few seconds. It's not much.